All right, well, thank you, Almadena, and thank you for all your help as my advisor, and thank you to all of our wonderful professors here for making this department the wonderful, vibrant place that it's been. All right, so so I'm going to present my thesis here with this very wonderful, complicated title with lots of very boring sounding words in it. But I think it's actually pretty interesting, so hopefully you will too. So I'm going to start by quickly introducing sort of some background on what we're doing. I'm going to discuss composite materials and the field of non-destructive evaluation, which is basically what my thesis is helping out with, and give you some background on computer vision techniques. And then I'm going to take you through the algorithm that I developed, and then finally talk about some of the results that I've achieved. So as Almadena mentioned, I've been interning with NASA Langley Research Center for the past 10 months or so, which is out in Hampton, Virginia. NASA Langley is a really exciting, cool place to work. It's actually the original NASA Research Center from back before it was even called NASA, back before the idea of going to space was even an idea. And it was a major pioneer of early aeronautics research. It was the training site of the original Mercury astronauts like John Glenn, active through the Apollo program. And then today there's lots of really exciting work going on there, particularly in fields like material science, which I'm going to speak more about, as well as robotics, earth science, aerodynamics, and a lot of other really cool things. And I wanted to share this picture I just found the other day because I thought it was cool. This is Amelia Earhart visiting NASA Langley in 1928, just after she returned from her first transatlantic flight. I thought that was just a cool little bit of history. But one of the fields that Langley has really been a pioneer in is the field of composite materials. And so composite materials, as the name suggests, are basically materials that are composed of more than one thing that have sort of been combined. So the most famous example is probably carbon fiber. So in carbon fiber, they basically take these carbon filaments and weave them together to form sheets. And then they glue these sheets of carbon filaments together to form a material. And these are really important for anything that's going up into the air or out to space, because they can be very light but very strong. Metal is very strong, but it's heavy. And when you're trying to send things up into the atmosphere or out of the atmosphere, heavy is bad. So there's a lot of focus on trying to develop new materials that are light and strong and have good heat-resistant properties. And for example, the Boeing 787 jet, which recently launched in the last year or two, is the first commercial jet to be 50% composites. And most spacecraft these days are very large, largely composite. But this panel you see there is a testing panel of carbon fiber. And in order to understand the properties of these kind of materials, they need to test them. So they simulate impacts with different kinds of materials at different kind of speed, and they want to know what has happened to the material. So here they've hit this carbon fiber panel with a piece of ice traveling at 500 feet per second, and we can see that there's some surface damage to the material. But what we really want to understand is what has happened internally inside the material. And that brings us to the field of non-destructive evaluation. And basically the idea here is that we want to analyze the damage to something without taking it apart. So if you've ever had an X-ray, you should be very familiar with this idea. You know, if you go to the doctor, go to the dentist, I think you'll agree it's much better to just get an X-ray than to have them cut open your arm and start digging around to see if you have a broken bone. So the same thing applies for materials. This allows them to do repeated tests and examine how the damage changes over time and with different kinds of impacts. And there's a lot of different techniques for doing this, but the one that we're going to be most interested in today is CT scans. The CT scan you can think of basically as like a three-dimensional X-ray. So here's one image of a CT scan of a carbon fiber sample similar to the ones we just saw. And with the CT scan, this is one frame of it, but there would be different frames representing a little bit further into the material, a little bit further to the surface. And so you can kind of see how the damage changes as you move through the material. But if you look sort of right in the middle of this here, you see this little oval. And that is the damage to this piece of carbon fiber. And that's called a delamination. A delamination basically is where the layers of carbon filament have become separated from each other and form sort of an air pocket. And that's bad because it significantly weakens the structure of the material. But as you can see, it's not that easy to see this, even just as a person looking at this image. You can see it's a little bit darker than the area around it, but there's other areas of the image that are quite dark, and there's not really any like easy to see edge to it. And it's actually hard to even get an image to the point where you can see it easily like this. You have to tweak the contrast settings and kind of adjust a lot of different sliders to get it to the point where you can easily visually see that. And so that's kind of a problem, because one CT scan can produce hundreds or even thousands of images like this for one sample. And currently, there are people sitting in front of computer monitors looking at pictures just like that, trying to basically outline the damage, understand how big it is in each image. And it's really not fun. And it can take days or even weeks for an expert to look through just one sample and do this. And this really impedes their ability to make progress, because if they make some change and test a new sample, they have to wait a few weeks to analyze it to see what kind of result that had. So we would like to find a way to automate this analysis and come up with some kind of technique that can just analyze these images with a piece of software that can identify this damage. So computer vision and image processing it's a very robust, well-developed field. There's lots of really cool stuff going on in computer vision. If you're on Facebook, you'll notice that in the last couple of years, they've started, if you upload an image, it'll actually recognize who is in the image. It'll tag them automatically based on facial recognition. So there's obviously a lot of very advanced stuff going on. And it seems like maybe we can take some of these tools that already exist, and apply them to our problem. So some things that you might think would be good approaches would be things like thresholding. If we know that our delaminations are darker than the rest of the image, maybe we can just set some threshold for the pixel value where if it's below a certain level, that could be damage. But it turns out that doesn't work very well because these images are very complex, and different parts of the image might be even darker than our damage. You might think we can do edge detection. There's a number of different algorithms for detecting edges in images, often doing some sort of like derivative or second derivative test, where it's basically looking for a significant change in like the slope of the pixel value. But our delaminations don't really always have clear edges, so that doesn't really work. Blob detection is going to try to recognize sort of objects or things that are sort of distinct from the surrounding area. But again, our delaminations they're not that different from the rest of the material, so it makes them hard to find. Morphology is a similar technique. And then you might think, well, what about some supervised machine learning techniques? Maybe we can train a neural network to identify these. And so we tried that, and it didn't really work. Basically, these images are very complex, and they vary a lot, and delaminations vary a lot from image to image. And if you're trying to train a classifier like that, it's difficult, because when there's so much variance between what your delaminations look like and with what the background looks like, it's very difficult to get something that's going to be generalizable to a lot of different types of materials and images and samples. Although there are possibly some further research paths in that area that could yield interesting results. But in general, these traditional methods are failing. Basically, because these images are very noisy. These are extremely noisy images compared to something that you would take even like with your iPhone camera or something. And there's just so much difference from image to image that it's very difficult for these techniques to work across all images. So my proposed algorithm is based on regression. And basically this is an anomaly detection approach to the problem. So I'm hypothesizing that the general carbon fiber material has a sort of general trend that we can identify. And the areas that are damaged are going to be areas that deviate from that trend. And so if we can identify what the trend is and then identify the areas that deviate from that trend, we can find our areas that are anomalies, and hopefully that's going to be our damage. So this is relying on the technique of regression. I don't know how many of you have studied this in statistics or economics maybe. But basically, with regression, you're trying to fit find a function or a model that fits a set of data points. So a really simple example, here these circles represent some data points. You can look at that and you can say, clearly these circles are clustering around a sort of a line here. And if I asked you, where can we expect the y to be for x equals 11, you can say, well, it's probably going to be up here somewhere. So with a regression model, you can basically fit a function that's going to find that line. And the way it does it is it tries to fit a function and it tries to basically find your coefficients that are going to minimize the squared error of the difference from each point to the line. And so you can do it with just a straight line like this, or you can fit higher order polynomial functions. And a really nice thing about this is that there's lots of programming languages, such as R, which I used for my project, which already have these kind of functions implemented, so you don't necessarily need to worry about all the mathematics and statistics under the hood. You can just kind of use functions that are able to do this. But one problem with linear regression is that it assumes that our noise is normally distributed. Basically, it assumes you're going to have like a bell curve of points distributed to either side of your regression line. And that makes it very sensitive to outliers. So here I've taken the exact same data points, but I took two of them and I dropped them down here. And maybe something went wrong with whatever sensor was producing that data, and it gave these these examples, or we don't really know. But now when we fit our model, it doesn't do nearly as good a job of modeling really what the trend of this data is. And now if I ask you what's the y value for x equals 11, you're going to be pretty far off. And that's a problem, because we are expecting our data to have significant outliers. In fact, we're relying on that, because it's those outliers that are going to allow us to find these anomalies. So we're going to need to use something called robust regression. And this is robust against outliers. Basically, the idea is it's going to find the trend of the data points while ignoring these big outline points. And you can think of this basically as iterated linear regression, where basically you fit your regression model and then find what was the biggest outlier and then sort of remove that or downweight it in your model and then refit with your new values. And you're going to keep doing that until you find a good fit, or until you hit some max number of iterations. And so you might be wondering, well, what does that mean for an image? How do you fit this kind of model to a picture? Well, basically what we're going to do is we're going to look at single lines of pixels. I'm going to look at an individual line of pixels here in the y direction, and I'm going to look at all of the individual lines of pixels in the x direction. And you can plot the values, the grayscale values of these pixels. And basically, darker pixels have lower values, brighter pixels have higher values. And so this line here is running through our delamination, which you can kind of just barely see here. And you can see here is where the delamination is. You can see that we've got this steep drop in the value of those pixels. So we're going to fit a 5th degree polynomial regression model to that. And then there's ways you can fit basically a prediction interval around that line, where basically you're saying that based on the properties of your data, you're expecting that 95% of your points should lie within these two red lines. And if it falls outside of these red lines, then you've got outlying points. So I'm going to fit these for every line of y pixels and every line of x pixels. And that means that each pixel is going to be represented in 2 signals or traces. And if it's an outlier in both of those signals, then I'm going to say there's something weird with that pixel. You know, I think that's an anomaly. So some nice benefits of this technique are that it doesn't require any kind of training set the way that a supervised machine learning technique would. So we don't necessarily need to know exactly what we're looking for. And so, you know, we might find delaminations, we might also find new types of damage that they didn't even know were there. It's also faster than a lot of other unsupervised techniques. It's very easy to parallelize. So if you've got a lot of cores, it's very easy to spin this out to multiple cores. Also very easy to take advantage of GPUs. One drawback is that it's going to identify anything that's sort of different about the material. So often that's something we're interested in, but sometimes it might be something that's different but that we don't really care about. So how well does it work? Well, if we just run this on the image and identify the outliers, we'll get a plot that looks something like this, where the black pixels represent pixels that were outliers in both x and y dimensions. And you can see this has done a pretty good job of finding this. We've also got some noise. But this is actually a pretty easily visible delamination. And so for less visible ones, like here, where you can't even really see it, it doesn't do as good of a job. You can kind of see maybe there's a cluster of points here, but you know, it's not really clear exactly what's going on. So we need to find some techniques that can help us do this a little bit better. So one thing we can do is smooth the image. As you can see, these images are very, very noisy. You can see in our delamination right here, we do have some dark pixels, but there's also lots of dark pixels in the rest of the image. And there are some light pixels within our delamination. But we can apply basically a mean filter, which basically means for every pixel, you take that pixel and you draw a box around it. We're going to draw a 41 by 41 pixel box, calculate the mean value for that box, and we're going to set that as the new value of our pixel. When you do that, you get an image like this, which fortunately doesn't show up super well on the screen here. But you can kind of see it's a little bit more obvious that this is all more or less the same color of gray, and then the middle is a little bit darker area. We're also going to apply a technique I'm calling Trough Identification. What we found is that for very light delaminations, only a handful of pixels might actually be identified as outliers. But if we have surrounding those pixels a trend where there's a lot of pixels that are below that regression line, they're not necessarily outside of the prediction interval, but they're all below that line, that means that there's something going on there that's a little bit darker than normal. So whenever I find an outlier, I'm going to examine the pixels around it. And I'm going to start seeing if they fall below that regression line. If they do, I'm going to say, okay, that's an outlier too. And I'm going to keep examining those pixels until I hit a pixel that is above that regression line. And then I'm going to stop and I'm going to say, okay, we found sort of the edge of this darker area. And so that'll produce results kind of like this. This is our raw image. If we were just running the regression without the smoothing or trough identification, we get this. You bring in the smoothing, all of a sudden you've done a much better job of finding it. But it's still not quite finding sort of the entire structure here. And so with the trough identification, it's doing a better job of finding sort of the entire structure of that delamination. Now, you might look at this and you might say that this is a little bit bigger than that maybe. But it's very hard for humans to kind of look at these and draw lines around them. If you have two people look at this and try to segment out where is the delamination, you're going to get two different segmentations. And so in general, we're going to err on the side of finding bigger areas than actually exist, rather than possibly finding smaller areas or missing them altogether. Because you can imagine if you're flying in an airplane or a spacecraft and they're examining the panels for that, if they take a panel and they say, okay, this is damaged, and they throw it out, even if maybe the damage wasn't that severe, it's not that big a deal. If they take a panel and they say, okay, this is good to go, when there's actually damage in it, that's really bad. So we're definitely going to err on the side of maybe finding larger anomalies that actually exist. But we found that what we really need to do is we need to run this algorithm 3 different times with slightly different parameters. So the first time I'm going to do what I just described. I'm going to smooth the image, I'm going to run the crosshatch regression, and I'm going to do the trough identification. And that's going to find basically every area of the image that might possibly be a problem. But it's probably going to end up finding areas that are too big. Because you can imagine if you have like a very dark, very easy to see anomaly, when you smooth it, it's going to make the edges, bigger than they really should be, because you're smoothing out that really dark area across a much larger area. And now you've turned maybe a small but dark anomaly into a much bigger thing. But we are identifying pretty much any potential region of interest. Then I'm going to run my crosshatch regression again, this time without smoothing and without doing the trough identification. So here, I'm just going to find the things that are really, really big outliers. They're really like, the things that jump out at you are very easy to see. I'm then going to take all of the pixels that I find in that run, I'm going to remove them from the image. And now I'm going to smooth that and run the crosshatch regression again with the trough identification. And that's basically going to find the minor anomalies. And so in run 2, we basically are finding anything that's like really dark and easy to see. In run 3, we're finding the things that are really hard to see and are really subtle. And then I'm going to require a pixel to appear in that first run, and then one of these two, in order to be considered a true anomaly. And so basically what this has accomplished is now when we have a really dark, easy to see area, rather than like smoothing it out so it covers a really big area, we're only going to find sort of the actual really dark pixels. But when there's a really light area that only had a few pixels that were actually anomalous, those pixels aren't, most of the pixels are going to stay in and are going to be identified in this run. And so this is going to do a good job of finding things that are very dark and easy to see, and things that are pretty light and pretty hard to see. Okay, so we've got this algorithm. Now we want to understand how well is it actually working. So first off, we tried running it on just real images that myself and one of my colleagues in the department, we had gone through and kind of segmented out where we thought the delaminations were. And then we ran the algorithm and we tried comparing the algorithm to what we thought. But that proved to maybe be not that great of an idea, because we started disagreeing about how the algorithm was actually doing. Because I would run it on some of the images that that we had done, and it would give different results. But then I'd say, hey, how do we know that the algorithm isn't actually doing a better job than we were? How do we know that we were right? And also it was bad because we couldn't really quantify how we were performing across different sort of degrees of anomaly or different shades of delamination, because we were just kind of using these real images. So we said, all right, we need to go back to the drawing board. We need to find some images where we know exactly where the anomaly is and where we can quantify these things a little bit better. So a researcher in the non-destructive evaluation department at NASA put together some simulated images. Basically what he did was he took a real CT scan of a carbon fiber sample with no damage. And then he also segmented out some delaminations from a damaged piece of material. And he basically pasted these into this background at varying sort of shades. And I'll show you in a minute a little bit more what that looks like. But this is going to be better, because now we know exactly where the anomalies are, because we put them in there ourselves. Okay, so how do we evaluate our results? We're going to look at a number of metrics. One metric is precision, which is basically measuring how noise-free are the results. Basically, of the things that we are saying are damage, what percent actually is damage, and what percent is false positives. We're going to look at recall, which is basically saying what percentage of the anomaly did we find, Did we find 50% of it, 75%, 0%? We're going to look at the root mean square deviation of the boundaries. That basically means for each pixel along the boundary of what I'm saying is a delamination, how far away is that from a pixel on the boundary of the actual delamination? And then we're going to look at something called Hausdorff Distance, which is basically saying, what is the furthest distance off that we ever were? If we have our what my algorithm has said is the anomaly, and what we know is the anomaly, what's like the furthest distance away that we ever got from the real anomaly? Okay, so here's a picture of one of these sample images. And this is where we've got the delamination at the darkest, easiest to see intensity. But I'm going to take you through this image and the results for each of the different intensity levels. So keep in mind where that is in this image. And now see if you can see it in this image. There's an anomaly in the same place. It's right about here. But it's been pasted in there just very, very light level, at a level that even for a human is maybe 50-50 whether you can actually see it. And this is what my algorithm has identified there. So it's doing pretty well. It has actually found that there's an anomaly. Maybe it hasn't found perfectly what the boundaries are, but it's identified more or less the size and location. Now we're going to make it a little bit darker, maybe a little bit easier to see. You can see it provides slightly different results. Make it a little bit darker, a little bit darker. As we keep making it darker, you can see the results start to get very close to what it actually looks like. So that was a pretty good result. And so we did this for 28 different samples, each of which had 7 different intensities. So we've got 196 images, and each of which had 2 delaminations. And basically, we successfully identified 92% of those. And that included 100% of the darker 4 levels. And basically, 2/3 of the ones that we missed were at that lightest, that level number 1. And we also had 0 false positives. So we never once identified an area where there was nothing at all going on. And here's what the metrics look like for the 7 different levels of intensity. And you can see, our average precision was 78%. That means that of the pixels we identified as anomalous, 70% of those actually were anomalous. 88% average recall means that basically of the actual anomaly, we identified 88% of the pixels correctly. The border of what we identified versus the true border varied by only about 11 pixels on average. And we were basically never more on average than about 50 pixels off, which is pretty good. Most of these anomalies are maybe somewhere between 100 and 300 pixels wide, or bigger. So these are very promising results, particularly when you look at this last one, where you see that the vast majority of our misses are at this lightest level, where even humans looking at those images are going to be missing probably at a similar rate. But yeah, so far we're very encouraged. We're successfully identifying an anomaly almost all the time. And our recall is very good. We're almost always identifying almost the entire shape of the anomaly. And if anything, we're erring a little bit on the side of over-grabbing it and identifying a little bit too big of an area. But that's not too big of a concern for us. Some challenges. When the anomaly is really, really big, paradoxically, that actually makes it a little bit harder to find. And the reason there is that we're looking for anomalies. We're looking for something that's different from the background. And when you have an image where the anomaly takes up most of the image, it's not different anymore. It's not an anomaly anymore. It just is what is the picture of. And so that's kind of what you see here. This is not a cutout of a larger image. This is the entire image. And you can see, the X signal through here, about 40% of it is actually going to be made up of these anomalous pixels. And so it's going to have a hard time finding those because it's not really an anomaly anymore. There actually are some techniques that can allow us to do that that we're going to explore in the future to do a better job on those. But the good news is those don't really matter because when it's that badly damaged, they don't even really look at the CT, right? They can just kind of look at the sample and say, this one's broken. And sometimes we're missing like these very small or very light anomalies. Okay, now you might be wondering, we've talked about this as an anomaly detection algorithm. We see that it can kind of work on these carbon fiber samples. Well, what happens if we apply it to other kinds of images? So I was wondering this too. I was reading a research paper that was talking about the problem of identifying pictures of boats in the ocean. And they said, this is sort of an anomaly detection problem. Where obviously you have this trend where we've got some water and some sky, and a boat's going to be different. So I said, well, I wonder if my algorithm works on that. And so I ran it and got a pretty good result. So then I started looking around for images that were maybe a little more complex. I found this one online. And I think this is pretty interesting because there is quite a bit of variance in like the shade of the water. Like it's pretty light here, it gets pretty dark over here. We've got some light and dark spots interspersed. And so I was curious, what was going to happen if I ran my algorithm on this picture. And that's what we found. So that's pretty cool, I thought. And so then I thought, all right, well, what if we make it a little harder? Can we find something that's trying to hide? And so we've got, a lion here that's sort of camouflaged into the savanna. And so I ran my algorithm on that, and we found it. And so I figured that if this whole sort of NASA thing doesn't work out, we've got a good market for the startup here advertising to gazelles. Very interesting. Okay, so that's kind of where we are right now. So what's next? So I'm planning on continuing to work on this algorithm for the next few months while I'm still at NASA. And we've got some ideas for ways we can improve it further. I'm going to look into using spatial statistics and some supervised machine learning techniques to help understand these anomalous regions once they've been identified. So once we have run the algorithm and have identified the anomalous areas, now maybe we can apply a neural network to start to classify those anomalies after they've been identified. I also want to look into ways to help detect sort of the boundaries of the material. So in all these images I showed, the material made up the entire image basically, right? But there are some structures that are more complex, especially a lot of like 3D printed structures. It's like a big area right now, 3D printing. You can create these very elaborate sort of structures with different kinds of like trusses and stuff going on internally. And if we can find a good way to identify sort of where those boundaries are of the material, then this technique might allow us to analyze these more complex structures. And then finally, we need to continue experimenting on more data sets, representing different kinds of materials, different kinds of carbon composites, to make sure that these results are generalizable beyond sort of just the data sets that we've been looking at. So I'm excited to continue working on that for the next few months. And the plan is to ultimately deliver a tool to the non-destructive evaluation group at NASA Langley that will allow them to just do this analysis so that they don't have to waste all their time looking at these pictures. And so that's kind of where we are. And so thank you all for coming. I'm impressed we had such a good turnout. And thank you again to our wonderful faculty here. And yeah, if there's any questions, I'd be happy to answer. Yeah.
What advice do you have for students who might want to work at NASA?
If you want to work at NASA, a great way to start is by being an intern at NASA. They have a really cool internship program, and you get to work on really exciting problems, but you also get to see lots of cool stuff. And yesterday, was it yesterday? Yeah. I just flew here, and I'm sort of very confused about what day it is. Yeah, I got to hear an astronaut speak about sort of his experiences yesterday. That was pretty exciting. But yeah, they have a great internship program, and I would say to get into that internship program, and from a computer science perspective, you basically need to have good coding skills, and then it's also good to have like some statistics, because that is an area that is pretty big in a lot of what they do. So if you have a good coding background and also some math and statistics, that's kind of what you need to be a pretty competitive candidate. Susan?
So while I was reading your thesis and you talked about looking for things in the ocean, I thought of, they were forever looking for that plane that disappeared. And if you can find it by scanning, that would be great.
Sure, yeah, I'll look into it.
Have you tried?
Yeah, I don't know what kind of, that's a good question, because obviously they have some sort of sonar or whatever they're doing for the bottom of the, I have no idea what those.
But then I think they were working on top of the ocean for like parts, things that drifted.
Yeah, that's actually the kind of problem that this algorithm might work for. If you basically had like satellite shots of like the ocean, and then you maybe have some waves and stuff, but then there's something, I think there's a good chance it could.
Right. I thought of that, and I thought you should, if you have the data, you just, how you just run it.
Yeah. Yeah, I'll have to see if I can.
Because I think they look for months.
Yeah, that's a good idea. Rachel?
Was there a reason that you chose to use R instead of using something like Python and other libraries?
That's a very good question. I have a very fraught relationship with R as a programming language. I am using R basically because when I came in, the person who I was sort of working with was a statistician, and he was very familiar with R, and so he said, all right, can we use R? And I had a little bit of R myself, so I said, sure, let's do that. Pretty much, you could easily do this in Python. Python has wonderful statistical libraries. NumPy and SciPy are fantastic. Honestly, if I was starting over, I would probably do it in Python, because I think Python makes a lot of things a little bit easier than R. But there's a lot of languages. MATLAB has great tools for this as well. And then, yeah, I mean, there's a variety of things. But Python in particular has a lot of excellent libraries for this kind of thing.
So the tool you'll be delivering will be in R?
Then? It will probably, the GUI part of it probably would not be written in R. Generally, most of the people at NASA are engineers, and they all use MATLAB. It's kind of like the main tool for engineers, and they're all very comfortable working in MATLAB. So I think the idea is we're probably going to write some sort of front end using MATLAB that'll sort of call the back end that sort of runs the R algorithm, and then they'll be able to analyze. Once they get the results back, there's more work that they then will do in MATLAB sort of to further analyze the results.
Is your project copyrighted by NASA, or can you sell it?
Yeah, so it's the code base belongs to NASA. So, I would love to post it on GitHub or something like that, but there's this sort of massive bureaucratic nightmare you have to go through to do that. And so we'll see. Maybe I'll be able to do something like that. But it is actually something that they are interested in having other people use, because NASA obviously works alongside Boeing and Lockheed Martin and all these other companies like SpaceX, and a lot of those companies have similar problems, and NASA's partnering with those companies in a lot of areas. So I think NASA does envision, if we actually get something that they're say, this is great, this works, we're good to go, it is something they would probably want to be providing to their partner companies as well. So possibly someday we could see some sort of launch for it. Yeah.
I was just actually thinking about the areas that you said the algorithm didn't do as well, so it was very, very light. So one of the criteria you have a three-phase thing where it has to, after you smooth it, it has to be that.
Yeah.
But by smoothing it when it's very, very light, you actually lose it in some sense, right? So could it be that, that technique, you have the three-phase criteria that has to be satisfied first, and then one of the two others, maybe the criteria need to change.
Well, I think there are sort of, additional layers that you can sort of add in to identify different kinds of things. In terms of the smoothing actually is sort of necessary to find the very light ones actually, because what we found with the very light ones is that basically you have a handful of darker pixels, but the vast majority of the pixels look the same as the pixels around them. And so when you smooth it, you do spread out those dark pixels a little bit, so now you've got a large area that is a little bit below where you're expecting. The smoothing helps with that, but But I think that there also might be better ways to detect those using, there's things you can do with like spatial statistics where you can basically say, all right, I've identified a handful of outliers, and you can look for clusters of outliers or areas where you've sort of identified more outliers than expected, and I think that's sort of another way you can maybe try to find those. Yes.
Also kind of on the algorithm end, I had 2 questions. The first was, so some of the noise, were there any patterns in it, for example, like with, that you could then filter out, such as like with the carbon, it's fibrous, so I don't know, is it kind of a repetitive fiber pattern that can be?
There's a lot of interesting patterns in these images, actually. Yeah, so there's, the one pattern you see a lot is, so the materials are woven together, and so sometimes you'll actually see the sort of, these straight lines representing, sort of, yeah, looking like a sort of patchwork of straight lines that are actually the material. The smoothing kind of takes care of that, actually, because they're close enough together that when you smooth it out, that kind of disappears. But there are a lot of interesting, there's some things that appear in the images that are kind of artifacts of the CT process, and it's a really interesting question. I don't really know the answer to it, but I think it actually is something that it's probably worth looking into to try to identify some of these kind of known kinds of noise.
Was anything done, by the way, in the Z direction? Or?
That's an excellent question. Yeah, so you might be saying we have these 3D images, why not take advantage of the 3rd dimension? And so initially that's what we were doing. The initial algorithm ran the Z signals as well. And we found, sort of when we were doing that, we found it wasn't contributing a lot of added value. But part of the reason for that was because most of the early data sets they'd given us didn't have that much depth. And so there are some data sets that have a lot more depth. And so I think that there actually is potential doing that with those data sets. One kind of bad thing about that is it hurts your runtime a lot, because to do the Z direction basically doubles the amount of time. And so that's basically why I sort of cut it out, because it wasn't providing value. But that's actually something I'm planning on looking into in the next couple of months too. All right. Well, thank you all very much.